Yay, learning.
Yay, learning.
You were saying?
Learning about the tide.
Do the same with me.
Learning about the tide.
Oh, someone.
The moon. This is a picture. Okay, my turn. This is a picture taken from the moon's surface, the lander and stuff.
Ooh.
There's a short section, 5.1, it's only a page long, that compares the Earth and the Moon. The Earth is a lot bigger than the Moon. The Moon, compared to the Earth, I have a moon globe here,
Rainbow power.
and here's the Earth. The Moon is actually only about half the size of this moon globe compared to the Earth. So if I had a tennis ball, which I don't happen to have up here, a tennis ball compared to the Earth is about the right size of the Moon compared to the Earth, if this were the Earth. And the Moon isn't very close to the Earth. Like if this were to scale, the Earth would be way over here in the corner, and the Moon would be over here in this corner. This is the scale. That's the true to scale distance from the Earth to the Moon. And remember, the Moon's actually about a half the size of this if we're doing a true scale model. And so it was quite an effort to get people on the Moon. It took billions of dollars and 10 years to plan out, and we shot rocket ships up there, and people walked on the Moon. It was amazing back in the late 60s, early 70s, and we've never been back again. It's been so expensive, not with any manned craft. But we did learn a lot of things about the Moon from our trips up there and our studies of it. Here are some of the properties. You can see one thing you might be interested in is surface gravity. The Moon has about 1/8 the gravity. No, wait, 1/6. Yeah, 1/6 the gravity of the Earth. So if you divide your weight by 6, that's how much you weigh on the Moon. So I'm 150 pounds. So 150 divided by 6. Anyone know?
25.
Very nice. State championship match?
Alright.
There you go. I'd weigh 25 pounds on the Moon. Means I could jump real far. Like I can't already, but even more on the So if you hit a golf ball, it goes 6 times as far. And even more so because there's no air up there either. There's no air to cause wind resistance and such. The Moon has no atmosphere. And the reason why that is because the Moon is so light that any gases that come out of the Moon do not stay on the Moon. They float off into outer space. If a volcano on Earth belches out a bunch of gases, they don't just go out into space because the Earth's got so much gravity. The gases stay down near the Earth's surface. Do you know what we call a bunch of gases down near the Earth's surface?
Atmosphere.
The atmosphere. So the Earth has an atmosphere because it's big enough to hold an atmosphere. The Moon doesn't because it's so small. The gases just float off into space. They aren't pulled hard enough onto the surface of the Moon. How thick is the Earth's atmosphere? Well, it's real thin. I mean, a lot of people, when they see videos and stuff that are talking about the Earth's atmosphere, those videos are all have very much exaggerated the size of the atmosphere to be able to show you the different layers and such. So you might see a video that shows the Earth like this, and it'll show the atmosphere real thick like that. And it'll say, here's the top, here's the stratosphere, the mesosphere, and the different layers. The Earth's atmosphere would be thinner than the piece of plastic that's covering this globe. It's real thin. So, it's still thick to us, but compared to the size of the Earth, it's real thin. It's about 6 or 7 miles thick. And after that, it drops off. It gets real thin, and not many molecules get up that high. So the higher you go up in the atmosphere, the thinner the air is. Because most of the atmosphere sits down next to the surface, because it's heavy. Kind of interesting stuff there. So this is even exaggerating. You see that light-colored thing right there? That's a big exaggeration. It's not nearly that. Of course, the Earth has a crust, this outer part that's solid, and then it has this mantle underneath it that's what they say that's semi-solid. It's kind of slow flowing. And then it's got this outer core down here that's liquid metal. Mostly iron and nickel, but a lot of other heavy metals too, like gold and silver. There's a bunch of it in the outer core, just kind of flowing around. And then the inner core is solid iron and nickel. And it's real hot down here. Crazy hot. And the pressure is real high pressure because all the gravity's pulling everything above it down. So the interior of the Earth is a very inhospitable place. Well, you don't find any living organisms or anything anywhere except on the very top of the crust. Maybe a little bit down into the crust, but not very far.
If the sun went out, could you heat yourself up by using that stuff?
Yeah, you could dig down deep until it got warm. And you'd be just fine and comfy if you could find the right spot. Yeah. And that's a big energy source too. Geothermal energy, it's called, is almost unlimited, and you just need to tap into it. A lot of buildings are starting to heat their buildings using geothermal. They dig real deep holes and inject water down into it, and the water goes way down and heats up, and then if they inject it with enough pressure, it'll come back up. And then now they got hot water, and they run hot water through pipes in the building, and it heats the whole building.
How far would it
Sounds
go?
expensive, doesn't it? It is. What's that?
How far would it go with those pipes?
How far down?
Yeah.
They don't have to go that far down to get warm.
How far is not that far?
Depends on where you are. In some places you might have to go miles down to get warm, and in some places you might have to go 50 feet down to get warm. So it just depends on where it is. So some places geothermal is not that right. Could be, it depends on where you are. Could be miles, could be feet. Usually when you get down in the ground though, it's at least starts to get warm, within a couple hundred feet. The moon is not like that. The moon has a crust also that's rocky. It's also got a mantle, but the mantle isn't semi-solid like ours. It's solid. And then underneath that, it gets a little softer here, and a little bit. There's a little bit more semi-solid material, and we think it's got a rocky core as well.
They dug down to figure that out?
No.
How'd they figure it out?
The way they figure it out is through quakes. There is a little bit of movement here of material, and every time there's some movement of material, it creates a little moonquake, like an earthquake. And they can set sensors on the surface of the moon, which the astronauts carried up there with them, that are still there today functioning, that can feel tremors. And by the speed of the tremors, they know what the interior of the moon is made of, by how fast the tremors move and in what directions and such. It's a very complex science. It's the same thing they do on the Earth. To figure this out on Earth, we use earthquakes. And the waves from earthquakes move differently through the different layers of the Earth.
Aren't those caused by the movement of the plates?
Yes.
So does the moon have
No, and the moonquakes are way less powerful than any earthquakes. They're just very slight, but they can still be detected by the equipment because they don't have plates moving. But there is some material on the inside of the moon that does move a little bit. So just moving material on the inside, just enough to produce. It doesn't take much. Those instruments are very sensitive.
So what's the deepest hole anyone's ever dug?
It goes down about 8 miles, I think, is the deepest.
Can people go down it?
Where would that be? What is deepest?
I think it's the Russians that are doing that science. It's a science experiment. The Russians also have a real deep one that's digging in Antarctica to a lake that's underneath the ice that hasn't been disturbed in something like 200,000 years. And they're drilling into it. The Russians are probably the best at
digging holes?
Digging holes, drilling equipment. Yeah, they have the best scientists with that. And
So can people go down that hole into the earth?
No, it's not a very big hole. It's like that big. And they just got to go way down.
Do they think it's like different wildlife?
Boring?
They don't know. They don't know what they're going to find in that lake. But it's a lake trapped in the ice. So there's ice, and then there's an area that's...
Why isn't that water frozen?
Because there's warmth under there. Because the interior of the earth is warm.
How far down is it?
It's like 3 miles under the ice in Antarctica.
That's awesome.
So it's like a perfect balance between the warmth and the ice.
Absolutely.
And the water.
That's it. And they're wondering that I think next year they're going to finish drilling. They've actually stopped right before it. And they're making sure they have all their ducks in a row because once they penetrate it, it'll come squirting out because it's under high pressure. And they don't want to contaminate it. You know, if there's bacteria or something on the drill head, and then it goes in there, and now you got bacteria in that water, and you might mistaken those bacteria for living things that were in the water. So the scientists are real worried about taking that next step, and some people are saying, oh, they shouldn't even bother it. It's been alone for 300,000 years. Who knows? There might be some weird kind of organisms living under there that no one's discovered. Big fish or something. Big blind cave fish. That would be cool. I don't know. It's fine that we talk about that stuff in astronomy, though, because it's exactly what they're looking at. One of Jupiter's moons is called Europa, and it's an ice moon, like the planet Hoth from Empire Strikes Back in Star Wars. It's ice all the way around. The whole moon is ice, water ice, and they know the interior is hot, and we'll learn why. So somewhere between the surface and the interior, ought to be a liquid ocean. A huge ocean, many times larger than the Pacific Ocean. Full of who knows what. Maybe there's nothing in it, but maybe there's fish and stuff. Living in Europa. Isn't that cool? Love this stuff. We'll talk more about that later. Let's talk about the tides. You ever heard of tides before?
Nope.
We have a high tide and a low tide. And why is that? Well, that's what I'm going to try to explain. This is going to be the sun. Okay? I'm going to put the sun over here. You pretend that's the sun. Now the sun would actually be way farther than this from the Earth. But yeah, you got to use your imagination. Now here is the moon. And here's the Earth. And you can just set it right here. Thank you. And so for right now, can I borrow this too? For right now, let's say the moon's still. Let's say the moon's not moving. And here we are on Earth, and I'll put a little tack to represent us on St. Simon's so that y'all can see. Ooh, let's make it a red tack so you can see red. Alright. So here we are on St. Simon's Island, and the Earth's spinning, right? Spins around. How many times does it go around in one day? What's that? Once, yeah. It goes around once a day. That wasn't a question. So here we are on Earth, and here's the moon. Now the moon has gravity, and it's relatively close. So the moon's gravity pulls on the Earth's oceans. And so what you end up with is a lump of ocean sticking out toward the moon. Now it doesn't come way out. I'm way exaggerating. It only comes up about 10 feet or so where we are. But it's a lump of water that's pointing toward the moon. And as the Earth turns like this, it goes this way, we on St. Simon's Island will move through the lump. And when we're facing the moon, that's high tide. And when we're pointed away from the moon, that's low tide. Now there's a lump that's facing the moon, but there's also a lump of water that's pointing away from the moon. There's a lump of water on the other side too. And that's kind of difficult for people to understand. So I'm going to demonstrate that. Ellie, come up here. You have long hair, that's what I'm picking up. You need someone with long hair. And you need to put your hair back behind your head. Ellie and I are going to do a little dance move. I'm going to swing you around. Now I'm pulling her towards me, but I want you to watch her hair in the back. Watch your hair as I swing her around. You ready? Don't fall. Watch your hair.
This is really
See it
strange.
going back? It's fun, isn't it? Stop. I'm busy. Thank you. Give Ellie a big round of applause. Did you see her hair going back? It's centripetal force or centrifugal force or whatever you physicists, you could probably tell me more about that.
That's interesting.
And that pulls the ocean as the ocean has a lump that's being pulled toward the moon, and in the back it has a lump of ocean that's going away from the moon because of the centripetal force?
This morning.
Centrifugal force? Okay.
Centrifugal does not exist.
Yeah, centrifugal, yeah. So here we go. High tide, low tide, high tide again, low tide again. Do you see? So there's 2 high tides and 2 low tides a day. But, and there's always a big but.
Is that funny?
Dirty joke.
Is that funny?
The moon is also moving, right? So here it is today, and it was high tide, and then low tide, and then high tide, and then low tide again. But the moon moves a bit, because the moon goes around the Earth once a month. So the next day, the moon is a little bit further this way, and so the high tide will occur about an hour later. Say it's actually like 45 minutes or 50 minutes later than the day before. Do you see? And then as the moon keeps moving, the next day the tide. So the tide, you have to almost have a table that tells you what time the high tide is going to be each day. Or if you know it one day, just add 50 minutes. That's when it's going to be the next day. And every day you got to add 50 minutes. I have a clock here, and that red handle tells me when high tide is. When it's pointed straight up, that's high tide. And that hand, that red hand, runs at a different rate than the other hands. Isn't that cool?
Yes.
It gets more complicated. And here they're showing that tidal bulge that moves the oceans, and this is, again, it's way exaggerated, but there's a bulge of ocean pointing toward the moon and away from the moon. Now, even more complicated is the fact that the sun has gravity too. The sun is real far away compared to the moon, but it's also real big. So it's got a little gravity too. And if you completely removed the moon, you would still have tides caused by the sun. They wouldn't be as intense. But as the Earth turns, you would have 2 high tides and 2 low tides a day caused by the sun. If the sun and the moon are in a line with one another, the tide is especially high. And that happens whenever you have a new moon or a full moon. They're in line with one another. And then you get especially high tides. So every new moon and full moon, we have an especially high tide that we call a spring tide. It happens twice a month. And that's when the tides really come up. And you might say, gosh, the tide's really high today. You're going over the bridge and it almost completely covers the marsh. Sometimes it comes up onto the causeway. If you'll notice, the next time you see one of those, look and check what the moon is. It's probably either a full moon or a new moon, but the moon's on the side. And when the moon is at a right angle, you have tides, but they're not really that high. We call them neap tides. They're the lowest change in tide differential between high and low tide is what we call the neap tide, N-E-A-P, when these things are at right angles to one another. But when it's all lined up, it's especially high. Then you have to add into the whole equation that the moon is sometimes closer to the Earth and sometimes is farther from the Earth in its orbit. So you'll especially have really high tides if the moon is close to the Earth in its orbit, and you'll have smaller tides when it's farther from the Earth in its orbit. And that's something that's even more difficult to predict. But scientists can tell you exactly when that's going to be and look that up on the computer. So here we see spring tides when they're all lined up, and neap tides when they're at a 90-degree angle. Now this is the coolest thing you've probably ever heard and you probably didn't know about. It's called tidal locking. Do you guys know that the moon keeps the same face toward the Earth at all times? That as the moon goes around the Earth, the same point on the moon will always point toward the Earth. And let me demonstrate that with, I need a piece of masking tape. With a piece of masking tape. I think it's this side. No, it's... Okay, see that piece of masking tape? That will always point toward the Earth. So the moon makes exactly one rotation to keep this piece of masking tape pointed at the Earth. The moon will have to spin once around on its axis to keep the masking tape pointed. You see it spinning. It's got to spin. If I do it like this, I have to spin it just in time with the Earth. Isn't that odd that it goes around once every time it goes around the Earth so that it keeps the same face pointed to the Earth? Don't you think that's an odd coincidence? McLean, are you getting any of this?
Yeah.
What are the odds of that? Well, the odds are exactly 100% that it will do that because of a phenomenon called tidal locking. See, the moon used to spin on its own, just like the Earth spins on its axis. But the spin of the moon is slowed down by the Earth. And it's a gravitational effect that's pretty interesting. But it causes this effect, tidal locking. And so, for the longest time, we didn't know what the back of the moon looked like. It was called the dark side of the moon. Even Pink Floyd made an album. Y'all still listen to Pink Floyd? Is that Dark Side of the Moon? And so we called it the dark, and it's actually not dark all the time because sometimes it's pointed toward the sun. But it was the side we couldn't see, so we called it the dark side of the moon. We didn't know what was back there. We assumed it looked just like the front side of the moon. And then we flew a spaceship around it in 1967 or something like that and took pictures, and guess what? It would look totally different on the other side. And there's a good reason for that, too. Which I'll tell you about in a little bit. So, let me explain first tidal locking. Why does the same side of the moon always face the Earth? Well, it has to do with the fact that just like the moon stretches the Earth's oceans, which we call a tidal effect. A tidal effect is the stretching of the Earth, making the Earth actually shaped a little bit like an egg with two bulges on each end. Well, that happened to the moon too. The moon is shaped like an egg a bit because of the Earth's gravity. And the moon doesn't have oceans, but the rock itself is stretched by the Earth into an egg shape. And because it's shaped kind of like an egg, it slows down the rotation of the moon because the Earth's gravity is pulling a little bit on that egg shape. And I have a thing showing. Here's the Earth's egg shape. Can you tell that shaped like an egg? And there's the moon. And if you notice, the bulge doesn't exactly face the moon. It's turned a little bit. It's offset a little bit because the Earth is rotating, and the rotation of the Earth, the friction with the Earth turns the bulge, it turns the bulge slightly pointed away from the moon. We call that the tidal bulge offset. The bulge turns slightly away from the moon. And so the moon's gravity is pulling on this bulge a little bit harder than it's pulling on this bulge. And the whole thing has a braking effect. McLean, you don't seem to be getting any of this.
I am.
Up all night partying?
Probably.
Possibly.
What's your tennis coach going to say about
That
that?
hair suggests yes.
I'm up.
So imagine gravity pulling on these two bulges.
Nice.
It's pulling harder on this bulge. There's only a few minutes left here.
Sorry.
Gravity's pulling harder on this bulge than it is on this bulge because this bulge is closer to the moon than this is. And so what we're doing is we're yanking. This Earth's trying to turn, but gravity is yanking it and slowing the turn of the Earth. And so the Earth used to spin a lot faster than it does now. 2 billion years ago, one day was only like 10 hours. Now a day is 24 hours. In another couple billion years into the future, the Earth will be turning a lot slower because the moon is actually slowing down the turn of the Earth. And the same thing happened to the moon. The moon started out spinning at its own rate, and the Earth's gravity, which was so great, it slowed down the moon's spin and eventually locked it in place. Where now the moon isn't able to rotate any on its own. The only rotation keeps the bulge of the moon pointed right at the Earth. Eventually, the Earth will stop spinning too, and both bulges will be pointed right at each other. And so the Earth will only spin once a month instead of once a day.
Did you say one time that the moon was eventually gonna orbit, keep orbiting and leave the orbit of the Earth?
That's another thing you have to add in there. But the moon is getting further away, so in billions of years it'll fly away on its own. So this braking effect will be less and less. So the Earth, the moon might fly away. The moon might fly away before the Earth is stopped from spinning. I don't know the calculations.
I don't think you really need to worry about that.
But you're right. No,
We'll
once
be
the moon goes
deceased.
up, it won't ever speed back up. It doesn't have any way to speed back up.
The Earth stops spinning, so there's no more time.
Unless they figure out how to preserve our bodies.
There would be no more tides.
Eliza will be
You're
frozen.
right. There would be no more high and low tide. there would be on Earth an area that's pointed toward the moon that's always high, and then another area of the Earth would be always low.
What about the sun? You have the sun.
But yeah, there would be effects from the sun.
Very good, man.
But the Earth wouldn't be spinning, is what he's saying, Waylon. So you would have to think about the effects of the sun, but the Earth wouldn't be spinning through those tides. So you'd always have the same tide in your area. And so you have to think about these effects. They're going on not just with the Earth and its moon, but with every planet and all of its moons. And so there's complicated, some of the planets are spinning and some are not, and some are going faster and slower. The moons have an effect on all of this. And so that's what tonight's reading's about. That was a famous picture when the spacecraft came around the moon and saw the Earth. And they finally got contact back with the astronauts that were behind the moon. Because when the astronauts go behind the moon in their spacecraft, you can't talk to them. And so there was a several-hour period where they were kind of on their own. And then they came back around the other side and they could see the Earth, and that's when they got the communications back.
Did they know that was going to happen?
Yeah. They knew it was going to happen.
That'd be bad if they didn't.
If they didn't know. It would have been really bad if the spacecraft had crashed into the moon on the other side and they never came back. And then they'd always wonder what happened to those guys.
If they died, would their body degrade, or would they just sit there?
Not at all? It wouldn't degrade at all?
I don't think it would. Well, I guess there's bacteria in your body that would start eating you up. But they died too.
Have people ever died
Eventually.
on the way up to space?
A dog died, I think. They sent like a dog to space and like kind
I
of.
don't know on their way. Not while they're in space, but like the space shuttle blew up, and there's been several explosions like on the launch pad and stuff.
Have people died?
Oh yeah. And
Columbia.
Coming back into orbit.
What happened to
the space shuttle's blown up twice. Once going up and once coming back.
What happened on the Columbia mission? What caused it to explode?
There was some kind of metal ring that it was real cold, and then when it got hot, because when the engines fired, it got hot and expanded and cracked part of the craft, and some stuff leaked out and caused an explosion. So yeah, it's dangerous stuff. You got no guarantee when you're riding on top of a big rocket. Okay, we're going to continue talking about the dinosaurs. You can turn that off. I want you to read about tidal locking.
Who wants to say bye? Bye, Olivia.
And y'all have to tell me.
Bye, Sam.
Bye.
Bye, Carson and Scott.
They're talking about
Bye, Olivia again. Wow. Bye, Kathleen.
Zoom in on that face.
You can dig
Bye,
on the ground
Phil.
if you're okay. That's the last thing I
Bye, Carla.
Bye.
Bye, Waylon.
Yeah, I'm gonna throw this mint at your face.
Bye. Oh, Daniel. Literally so
Just
sexy.
more on camera.
I'll live.
Hello.
Throwing this mint
Okay,
at
bye.
your face.
Okay, bye, Ellie.
I've
That
warned
was
you
some good
twice.
dancing.
I've warned you twice.